Hi, welcome. So, we've been talking about the effect of Prandtl number, and we went at length to understand a few things about that. So, if we were to kind of remind ourselves a little bit, okay. So, say we have okay. So, this is the flat plate. For some reason, not able to. Okay. Now, I'm going to draw an axis system. Okay, and then I'm going to draw three things here. That. Okay. Now, what we have coming in is the free stream, right? So you have free stream coming in, right? And let's say the temperature of this surface is given by, Ts, okay? Now, then this actually, this blue line, okay, now that is essentially the velocity boundary layer. That is the velocity boundary layer, okay? And say at some location, right, at some location, okay, this is the height of the velocity boundary layer thickness, okay? And both these are also thermal boundary layers. The green and this are both thermal boundary layers. So, again, this is the thermal boundary layer thickness. Okay. So, what I am essentially saying is that this is also, this is a thermal boundary layer, so is this. This is also a thermal boundary layer. Okay. Then what is the difference? Okay. Now, why do we have two of these, and what do these things even mean? Well, the difference is that for the velocity boundary layer, okay, the Prandtl number is equal to 1. Okay. The boundary layer thicknesses which are less than the velocity boundary layer, we kind of did this yesterday, right? So, in the previous module, here it is greater than 1, and this is Prandtl number which is less than 1, right? So, essentially what you see is that if Prandtl number is equal to 1, then the velocity boundary layer and thermal boundary layer thicknesses are same, okay? If Prandtl layer is sort of, equal to 1. If Prandtl number is greater than 1, right, then the velocity boundary layer thickness is larger than the thermal boundary layer, and if Prandtl number is less than 1, then the thermal boundary layer thickness is larger than the velocity boundary layer. Okay. So, again, to remind ourselves, the velocity boundary layer, right, that depends on the Reynolds number, okay, and the thermal boundary layer depends on both Reynolds number and the Prandtl number, right, both of these things. Now, for example, right, that, okay, so this is something that we've sort of, done this quite a lot earlier on, okay. Now, for Prandtl number is larger than 0.7, okay, then we get a relationship something like this, okay, and for very small Prandtl numbers, this, right? And this is a case, okay, this is a case where the Reynolds number is less than the critical Reynolds number, okay? It's less than the critical Reynolds number. And if the Reynolds number is greater than the critical Reynolds number, then okay, and that, okay. So now it's the same, okay, as the velocity boundary layer and thickness and the thermal boundary layer thickness are same, and the viscous dissipation. Now we're going to talk about dissipation, right? So now the point is that the viscous dissipation and high speed effects, okay, can be neglected, okay, can be neglected if, so let's just write that down here. So viscous dissipation and high speed effects can be neglected if Prandtl number right. So if the root of Prandtl number into the Eckert number and half of that is really very small, right? So we should be able to disregard the effects of dissipation and high speed. Okay, so now, however, what we're going to do now is that go ahead and look at the effect of dissipation. So far what we've done is we've neglected it, so we're not going to do that anymore, and we're going to see that when we cannot neglect dissipation effects, what really entails. Okay, so that's our job today. So let us go and see what that means. Okay, so now basically, so let me say this is effects of dissipation. Right, this is effects of dissipation. Of course, now, I mean, so far the effects of dissipation we have been neglecting that. Okay, now in regard to this, okay, the distribution of the adiabatic wall temperature becomes very important in the context of the effect of dissipation. Okay, so the distribution of the adiabatic wall temperature. So right, so the distribution of the adiabatic wall temperature becomes very important, and we're going to call this as okay, T subscript AD for adiabatic. Okay, now of course the first question is, what exactly is dissipation? Okay, what do we mean? What do we by dissipation, and why are we studying this in context of the thermal boundary layer? Okay, well, the point is that even if, right, so we have say a flat plate or any body, okay, if there is no heat transfer to the body, but due to the dissipation effects, right, due to the dissipation effects, a boundary layer still forms, right? A boundary layer still forms right, where there is a difference in the temperature, essentially meaning that there is a thermal boundary layer where the wall temperature becomes different than that of the free stream temperature, and therefore that kind of develops. So therefore a temperature field develops between the flow attached to the surface that we are talking about. So dissipation essentially means that there is really no heat, there is no heat transfer to the body in the flow. There is no heat transfer to the body in the flow. But due to the effects of viscous dissipation, right, there is a viscous flow happening. So as a result of that, okay, there is a thermal boundary layer develops, right, where the wall temperature is different, okay, and that kind of develops into a thermal boundary layer, so that it reaches the free stream temperature of a little distance away from some distance away from the body, and which is what we call as delta T, or the thermal boundary layer thickness, right. Okay. Now the point is, if the surface of the body is adiabatic, I think you understand what we mean by adiabatic. So now if the okay, before I do that, can I maybe I should just write what I meant by dissipation, right? Okay, fine, we'll do that. Okay, if the surface of the body, if the surface of the body is adiabatic, what does that even mean, right? There is no heat exchange across it, right? So there is no heat exchange across it, right? There is no heat exchange across it. Then due to the dissipation effects, right, there is no heat exchange across it, right? But so that's what you mean by adiabatic. However, in this particular case, due to the dissipation effects, okay, the wall temperature, okay, due to dissipation, right, the wall temperature increases above the surrounding temperature, okay. Due to this increases well above the surrounding temperature, right. Now, so the point is that there is no heat going in or coming out. There is no heat exchange happening. Okay, so in the sense, how do I kind of define this a little bit? Okay, let me first write down what exactly is dissipation, right? So it's in continuation of this. Let me just write. So even if there is no dissipation, okay. Even if there is no heat transfer to the body, okay, in the flow, due to the dissipation effects, right, thermal boundary layer is formed. The point is that you could just have, you know, just think about this, that you know, you take just a cup of tea, right? You just take a cup of tea, and you take a glass of water, right? You just take a glass of water, and now the glass of water is at room temperature, Okay, so you can put your hand in that and that's fine, you're okay with that. But if it's like really a hot cup of tea, if you put a hand in it, it'll burn, isn't it? So now the why is, so now if you hold the saucer or the cup itself, it's also warm, right, or at least hot. Okay, so now the thing is that if you leave this cup of tea, right, after some time the temperature will drop. Right, temperature will drop. Why? Because now you have the ambient temperature, or the temperature, the normal temperature is less than the hot tea, the temperature of the hot tea. So the temperature it's moving, right? So there is a certain heat transfer, right? Flows from higher temperature to lower temperatures, simple. So therefore, now that happens. So that's another way that that there is a change in the temperature. So there is a change in the temperature in the sense that the tea becomes less warm, and that probably around that, if you put your hand on it, it's just going to get warm, right, because there is a certain heat exchange to it. So that's the way a temperature can change. In this case, there is actually no heat exchange across the surface. Nothing of this sort is happening. Okay, but this dissipation is really the viscous dissipation. What do we mean by that? That this is also similar to the fact that if you take your two, if you put your palms together and rub against them, you'll probably see it'll still warm up a little bit. Okay, so it's probably a little crude way of explaining that, because you have layers of fluid. You've got layers of fluid on top of each other, right? And they are they are moving because of this viscous effects, due to layers, right? And it is this effect which causes a viscous dissipation, as a result of which, while there is no heat exchange across, the body in the fluid, right, there is still, due to this and this effect, this is the viscous dissipation effect, where even if that is not slow, right, that wall temperature, okay, increases above the surrounding temperature due to this viscous fluid wanting to move over the body. Okay, and therefore, and because of that, and since the wall temperature increases, there is a thermal boundary layer, because then at the temperature at the wall, okay, so temperature at the wall, of course, is this, and then so that decreases and this becomes T free stream, right? So this is basically, and so this height at which this sort of thing is happening is the thermal boundary layer. We sort of talked about that. So that's kind of what we mean by the effect of dissipation. So this is essentially viscous dissipation that we're talking about. Okay, so now let us do a little bit of math, because now all this is understanding now. So how do I get an account of this, right? So we'll do a little bit of math and see. Okay, now at the surface of the body, we'll define a temperature field. Okay, so at the surface, of an adiabatic body, the temperature field yeah, I'm going to define it like that, right? Okay, so this is essentially a capital theta. Okay, it's a capital theta. So so this is something how we define this. Okay, so then from the energy equation. Okay, now from the energy equation, we get Okay. That okay, this, right? And the boundary conditions are the following. So, the boundary conditions at the wall basically isn't that obvious, right? So, there is essentially no temperature field, then okay, and oh yeah, so here basically okay, it's basically this is equal to the free stream, so then we don't have one. Okay. All right. So then what we do is we essentially then solve this equation 2. We solve equation 2 for the wall temperature field. So what we solve for, then we solve 2, okay, for this, right, which is a function of the Prandtl number and location, so that we get an expression for the adiabatic wall temperature, okay, which is, we do this so that we get that right. So we do that. Now, so now obviously, so now what you see here, so what we can see here is that essentially, now this again depends on the Prandtl number. Okay, so we can see that now this depends on the adiabatic wall temperature, depends on the thermal boundary layer. So again, what we will do is that we'll go ahead and look at the two limiting cases, small Prandtl number and large Prandtl number, and see what that means. Okay, so let us do that and see what information we get. Okay, so we're going to start off with small Prandtl number. Okay, if I start with that, so that's my small Prandtl number. Now then here, so what we're going to do is, so let's keep this equation. So let's keep looking at equation 2. Okay. We're going to look at equation 2. So what we're going to set, so we're going to set theta bar by Prandtl number. Okay. So then we get, okay, if we do that, what we get is this. It's actually very interesting if you see this. Okay, just simple playing around with the equation gives you interesting information. Okay. Right. So what we basically do is we just set a theta bar, which is a theta bar, as theta by Prandtl number, and we just change that and put that into 2 here, right. So what we get is this. Okay. So what we get is this, and so we get equation 4. Now, so for a small Prandtl number, so therefore if small Prandtl number, what do you think happens if you look at equation 4? So then if you see here, the entire left hand side disappears, right, if Prandtl number goes to 0. So, this basically then tends to 0. Okay. So, then if that happens, then this equation, from the equation 4, what we get in that case, what we get from this equation is the following, that okay, so this we will do a very simple math to solve this, and right. So, that now what we will do is we will just do very simple math to work around this. Okay. Okay, so what we should do is integrate this, right. What I want to do is integrate this over, say, a very small elemental part of the boundary line. So, y bar. So, what I am going to do is, so what I am trying to say is we are going to integrate this over, say, a small height of y bar. So, then I am going to call that as dy bar, right. Take a small little element like that and integrate this thing. Okay. So, then if I do that, what I mean by that is this, that I say del 2 theta bar dy bar, okay, is equal to minus 2 dy bar, and we are going to integrate this, okay, that y bar is 0 and y bar is very large, right. So, again y bar is 0 and y bar is this, right. Now, we know, so if I do this, right. So, from here, therefore, what I can find, what this, if I integrate this, so what I will basically get then is del theta del y, right, the limits y to 0, that, okay, which is equal to minus 2 okay, del u star del y square dy. So, we will have that. Okay. Now, from the boundary conditions, now at y bar this, right, therefore, this is also equal to 0, right, and at 0, we just know, we're going to just say del right, just denote it like that, or so basically that. So, we're going to find that out. Okay. So, if I do that, so again from here what do we get? So if I do that, so the left hand side of this basically then becomes, let me continue here, that so at infinity, so if I go there, so what I will get here is, so this becomes 0, so I get 0 minus wall is equal to minus 2, 0, that. Okay. So, or so finally I can write this. So, or from 5 basically, right, from 5 what I can do. So, here essentially therefore the the negative signs cancel out. So, I can write, so from 5, okay, so del theta bar del y, right, at the wall is equal to 0 to infinity 2 del u star del y bar. That, okay, and this can also, so basically if I were to write this, then this will become 1 by Prandtl number at the wall, right? Isn't that so? So then this is something that I call as 6, right? This is an expression that I'm going to call as 6. Okay, so so we will discuss this a little bit, okay, when we come back into the next module, that what does this even mean, right? So now that if you do have, for very small Prandtl numbers, right, and we've taken into account the dissipation effects, so what does it, and we, as we just said, that this, in here, the wall temperature, or the thermal boundary layer thickness, will depend on both Reynolds number and Prandtl number. Okay, now we've used the energy equation here, and we've come up with the expression. We've come up with a relationship, okay, for the velocity field, okay, near the wall. So let us come back and look at this a little more in detail in the next model. So we'll stop here for the moment. Okay, thanks.